So exercise 59, this is firstly a corollary of exercise 58. So the statement is as follows. So we're going to only prove one direction, left other direction is a sub-exercise. Suppose we have a non-Archimedean norm. Normed field F, then F is locally compact. If and then if, I mean locally compact with respect to this norm on it. If and then if, all the three conditions are satisfied. First is that if it's complete. Second is that this non-Archimedean norm is discrete. Thirdly, residue field class is finite. So let's only prove this direction. By exercise 58. 1, 2, 3. Implies OF is compact. So, which means actually if I put a sub-exercise to show that actually this is if and only if, then we are down because we have proved this. This comes from, this is equivalent to the fact that it's locally compact. This is our exercise 57 should be. So exercise 58 tells you this is true. And let's put this as a sub-exercise to show that F is compact if and only if, which is only left to show that if OF is compact, then F is complete, the norm is discrete, and the residue field is finite. And let's solve some sub-exercise mentioned in exercise 58. So firstly, we have the one that mentioning if you have normed field, then all the elements with norm smaller than 1 is maximal. So in OF, defined to be those. With norm less equal than 1, and this is the unique maximum. Only maximum. So we show that for any element in OF that is not in N, we have some element B. By definition, its norm is 1. This implies that P inverse from F is in OF. Why? Because let's compute the norm of it. This is again 1. So what does this mean? This means that element outside of this M is invertible. So M is the unique maximal ideal. And I didn't show its maximal, but the same proof showed its maximal because after quotient the element is invertible. Okay, so this is a field. Quotient is a field, so this is maximal. This is a local ring actually. Second sub-exercise is that we want to show that Archimedean norm is discrete if and only if its maximal ideal is principal. So I use valuation. This is much easier to do. Okay, give a sketching proof. So let's talk about the valuation. I mean, valuation means you have a map from OF to Z, but up to normalization it's to Z. In general, it's to some over E is some integer of Z. Surjective. Up to normalization, you could just map it to Z, but okay. So up to normalization, you could suppose it's image is E, which means you just define your valuation to be E times whereas the valuation before, then everything maps surjectively to Z. And then this direction is obvious because just up to normalization you can map pi to 1, and then this will imply that any element am, say a to the power say a equals some power of pi, then way of a equals na, right? So, and in general element should be a unit of OF times such power of pi, but the unit has valuation 0, so it's this. So you see that all the valuation is discrete subset of additive group of R. And conversely, so if you have the image as a discrete subset of additive group of R, so up to normalization, let's say it's surjective onto Z, then take a pre-image of 1. Let's write omega pre-image of 1. Then any element A of F with A equals NA just by computer valuation, we have A must equal this omega bar to power n a times some element has valuation 0. And if you have valuation 0, u will be a unit, so times a unit. This shows that this element preimage of 1 actually gives you generator of maximum ideal n, and you can define pi to be this one up to multiplication by unit. Okay, so why this? If you have element whose valuation is 0, tells that u is a unit. So we have seen one direction with the similar argument as here. We have seen one direction is that if you have valuation 0, then you are a unit. Conversely, if you are a unit, and u times u inverse equals 1 implies that the valuation of u plus valuation of u inverse equals 0. But both are positive, not negative, and so both should be 0. Okay, let's sketch and proof of this. So what else do I want to say? Exercise 58 gave an alternative proof of the fact that QP is ZP is compact, and so in particular this gives as application to show another proof again. Another proof of QP locally compact. Which was already shown in exercise 57.